Okay, now it's on YouTube. Did you post the link?
Let's see. No, I didn't. Yeah, great. And I think I'm. Okay, let's see. Okay, good. Okay. Okay, so I think everything is good to go.
Okay, let's see how many people are in the place though.
Yeah, we can always just do questions and discussion.
Yeah, there's no questions though. Let's see.
Right. We can just do. I'm happy to just say stuff. I can.
Yeah, there's only 21. We gotta wait a bit. So we've been having about 150. So
Okay.
that's so it dropped quite a bit, right? I mean, as expected.
Yeah.
But
the great thing with this is I can have absolutely no, there's no expectations, and also part of the goal is to have these are physically now sort of permanent. Well, not physically, they're permanently here, which means like they're useful.
that's the great part about it. Yeah. That's the best part about it, I think.
I might try to, when teaching in the fall, I'm going to try to, I think I'll do this in the fall and have people just watch this and have a completely flipped classroom and just do math discussion. And I'll see how that works and whether younger students can do it in a way that they couldn't before.
Yeah, that'll be interesting.
The thing that scares me the most is I realize that we get trained to sort of watch stuff at double speed and to try to digest it really super fast. And that's really not the right thing for something like this. So, and the people who have the maturity to know that are almost by definition, not the people, right? I mean, I notice a lot of people who are currently present have the maturity to already know that. And it's the ones who don't know that, well, that will suffer.
Yeah.
Okay, so should I talk about a few things before starting?
Yeah. Go for it. I think we should start at 11:10, and then I think so there's 58 people. We'll probably double size. So yeah. I think you should explain how many lectures. Well, say how many lectures we have now.
So great. So before okay, great. So we're not officially starting. I'm just chatting with Taylor in advance so few comments about the experiment so far. The experiment's not supposed to be a perfect experiment, and I'm very aware that I'm I would love to sort of spend twice as much time on this, but I figure spending this much time is better than spending zero. I am happy with the discussion people are having. I'm less happy with my ability to participate. David Moulton says that I agree the pace is too fast for people with real jobs. But the good thing is I think I'm going to pause this for a bit or end this sequence of pseudo lectures in a few weeks, maybe 2 or 3 weeks. And that way people can fall behind and then maybe catch up.
I think there are a lot of people catching up because I've talked to students too who said that they're catching up, and I think
that's good.
A lot of asynchronous stuff going on.
Yeah, no, I think the good thing is I feel this should be partially synchronous and then partially asynchronous, and people can watch the lectures and digest stuff. And I also find it's useful to watch stuff that I only am half ready to digest because it's in my subconscious, so long as there's time to do proper digesting later on. So I think, well, actually, I might as well, we're not starting officially, but I'm going to update the slides a bit to say, I'm thinking that I'm certain we will end this round on the 19th or the 26th. I'm going to find a reasonable, I already have in mind a reasonable time to end or spot to end. And so the question is just where the material, where that ends lecture-wise. Then I think I'll pause for somewhere between 2 and 4 weeks so people can catch up, people can finish, they can conclude and talk about stuff. Other people can start later. And what happens a month later might depend a little bit on what the post-mortem is on this experiment as well. So there's stuff I think I might like to do. I'll also in advance advertise, I guess things can bifurcate or trifurcate now a little bit. I promised like you that I would do something on stacks for people who were experienced about it to maybe talk for an hour. And better than that, Jared Alper, who's I think one of the people in the world I would most want to learn things like that from. He's going to be giving a class in the new year, and he has agreed to tentatively do the thing I was going to do online. So in AGITTOC, at some point in the future, he'll do something for some people with no promises on anything. Anand Patel also had talked about giving little mini things about some of his favorite varieties that were intended for people thinking about them for the first time. So we'll do that soon. So he's recording some and trying some out right now, and we might as well stick them on this channel because why not? Because we can. And maybe if there are other things like Taylor's lectures on stacks or other people have given explanations somewhere, we could just link to them or put them in the playlist.
Yeah.
So that's what I'm thinking right now.
Yeah. Some people asked what we've covered so far. That was another question. So.
Great. Good question, but okay. So from my point of view, what we've covered so far, which may disagree, I think the person whose opinion matters is yours, not mine. And yours is not, I don't mean Taylor. I mean the person, the person at the other end of the screen. But what I think we've covered is, and will cover by the 19th to 26th, is completely what schemes and varieties are, including morphisms, and enough to be able to either have seen or be able to quickly read lots of stuff about morphisms. And so the basic language, but not things like cohomology or dimension, you'll already know. And that's in a total of about 12 hours, or actually more like 11 hours total, which is really not much time. So I bet some people are probably feeling like we got nowhere. But if I think about how long it takes me to get somewhere in a class, we've actually gone super far. So I'll say at the end more explicitly what in the notes I think we've covered. Today we're going to do things slightly out of order, for example, because I'm going to try a different order when I'm talking with people as opposed to having people read.
Yeah.
Great. 1 month
All right,
gap.
so we got about a minute left, and then I think we should start.
Great.
So yeah.
Okay. As long as we have another minute, I'll say like there are a few random small things, which is there's exposition I want to try out in things in the writing. So I figure one place to do it would be to give like a 1 hour random disconnected talk on associated points or associated primes, which I have to finish off. Eric Larson gave has figured out what I think is now the new canonical best proof of cohomology and base change. It's like a 2-pager that is just ridiculously clean. And it's amazing that I think it's probably true that it's better than what's in the literature. And so I've written that up, and maybe I'll explain that. Of course, I ask him to explain it, but I think I'd rather explain it so I can make sure
so explain it right. Yeah.
Okay, so
I think time to go. Yep.
Great. Okay, so welcome everyone.
I'm gonna leave here now.
We will officially start. So this is a new mic, so let me know if it's too quiet. Let me just zip in immediately to the math. I'm thinking, as I'd mentioned in the informal part before, that I will go for another 2 weeks or 3 weeks to the 19th to 26th. We'll take a break for about a month, and we'll declare victory with AGITTOC in general, and then there'll be a new separate thing starting next time. So people can leave and come back. And today, I want to talk more about morphisms and how to think about them well. And so this is we're in the setting of schemes now. Even varieties we're only partially in that setting, but I want to say this in a way that a lot of it will apply for things like complex analytic spaces or just general kinds of geometric spaces more generally. But in the notes, we're going to do things a bit out of order. We'll do chapters 9, parts of chapters 9, and parts of chapter 7. Okay, so let me just recall about morphisms, where we are with morphisms. So what's a morphism of schemes? Well, a morphism of schemes is going to be a morphism of of ring spaces that locally looks like things like maps of specs. Or if you want to deal with varieties, you're welcome to think of M spec still. So these are maps of ring spaces that look like this. And by look like this, I mean you take a ring map, and we've already figured out how to get a map of ring spaces in back. And so you don't need locally ring spaces for that. But we did like thinking about things in terms of locally ring spaces because it helped guide us with, on what the topology of this space is, what the Zariski topology was. And the last thing I'll say is you can also, just so you don't think it's all about these very abstract algebraic things, it's actually about abstract other things too. So complex analytic spaces are the other examples. You should just try to, if you're happy or semi-happy with the scheme story, then think about what we're doing fully in land of complex analytic spaces. Okay, so let me tell you remind you of a fact from last time, which is a really neat fact, and you may not appreciate, I don't know if you appreciate it yet, but I'm hoping you will appreciate it more and more, which is, okay, so the fact from last time is that the maps to an affine scheme are exactly the same as the maps in the other direction from the ring to the space of functions. So for when X is affine, that's our local model of how all maps of schemes are. But even if X is not affine, still we know what all the maps to an affine are in this way. And this is special about the target being affine, not the source. So this is going to be so important to understand. And so I'm going to use that to prove another fact, which is going to be another hopefully favorite fact of yours, that all fiber products exist in the category of schemes. And there's a bit of caveat, I should say, about varieties. So so this is the first time when I want to have when I need to, I should say a few words to talk about varieties, to extend it to varieties, and I don't want to just now, just for the sake of time. But let me make sure I remember to constantly update. Okay, so what does this mean again? The fiber product is whenever you have a diagram.
Hey, Ravi, one small comment is that
yeah.
Your cursor appears to be on the screen on YouTube, but it doesn't appear on.
That is good. I know what that means. So now it should be gone.
Okay, so I'll have to wait a little bit, but okay.
Yeah. Good. Yeah, no, I now know when that happens. I think it's strange, but I now know when it happens and how to stop it. Okay, so fiber product, just as a reminder, back from category theory land in the first week or so, is that anytime you have a map to X and Y, that give you the same map to Z, then that will give you, that will induce a unique map making all these diagrams commute. Okay, so in doing this, I'm going to try to get across not just that all fiber products exist, but some deeper understanding of something without saying what that deeper understanding is. So the way to think about this is a perfect example of Grothendieck's entire point of view, which is you understand things by just observing things and noticing things repeatedly, and just ratcheting up your understanding until suddenly you've gone far further than you have. So this is the image of softening. It's kind of a strange metaphor. I guess he's not a poet, but the image of sort of just softening and opening it up gently rather than hitting it with a sledgehammer. So I'm going to give you I'm going to try to explain the proof. I want you to please, the goal of this, some theorems, you see a proof, you nod your head, and you're happy that you know it's true. In this case, it's the actual means of proof that I want to get across. And I'm deliberately going to do this in a way where it's going to be in slow motion, in Grothendieck speed, where I want to do a bunch of small things in a row. And the result is something you really could say in 2 lines with fancy words. And then those 2 lines are best done only after you've digested it. So I might as well say the 2 lines now, just so it preemptively deals with your curiosity, which is basically, what's the definition of a scheme? Well, a scheme is a sheaf in the Zariski topology, in some sort of notion of the Zariski topology. So things that it's a scheme is something which locally looks like an affine scheme. That's even our definition. And so the fiber product is going to be a sheaf in the Zariski topology, and our proof is going to be that we're going to show it locally is represented by affines. And I could just say that and declare the proof done. And
Real quick, the cursor's back.
Ah, damn it. There we go. Cursor is now gone. I see. I'm going to be tempted to move that cursor in again. So you'll have to stop me again. Great. So great. So to say it again, you could say this in an officially correct two-line proof that some people would be very happy with is that the fiber product is sheaf in the Zariski topology will show us locally in the next slide. It looks like an affine, and therefore we're done QED. But that there's no the insight is all hidden. So please try to understand what we're doing. Okay, so I'm just going to make some observations, and I'll see how happy you are with those observations. The first observation I want to make is a really important one, even by itself, which is one kind of fiber product already exists, which is if you have an open embedding, if one of the two is an open embedding, if X is an open embedding inside Z, then this fiber product exists. Why? Well, because I can tell you what it is. It basically, what it's going to be is just the preimage of this open set. So I claim that this is that the fiber product is this, or in other words, this open set indeed represents, satisfies universal property. And why is that true? So if you think about it, the question you're asking about is you're looking for what are the maps? Maps to this mysterious thing are supposed to be maps to Y that happen to lie inside U. And if you just think of what that means, that literally means maps to the preimage of U. So because the maps like this and commuting give you a map like this and vice versa, that means we're done. There's nothing else to say. Okay. So that's my first observation. My second observation, now I see why the cursor will come and go. Let me see if I can help that. Okay, good. My next observation is that in the category of affine schemes, fiber products exist. So let me be a little bit
Hey, Robbie.
clear here. Yep.
It seems like you can only see half your screen.
Now that has happened before, and that has always been mysterious. Better or not better?
Not the same.
Oh, maybe better.
There
or
you
not
go.
better?
Now it's back.
That
Better.
is weird. Okay, good. Now I think I understand, and I believe you can see all the screen, and I think you don't see the cursor. Is that right?
The cursor is off to the top, but it's not on the actual slide.
Good, great. That's strange, but is it moving around? No.
No.
Good. Great, strange, but great. So I'm claiming next to the fiber product in the category of affine schemes exist. And just to be really clear what I mean, I don't mean, so we have two different categories here. And I'm not talking about schemes, I'm just talking about affine schemes. So I'm only allowed to talk about affine schemes and maps of them. So why does it exist? Well, what does it mean for it to exist? We're looking for, we have affine, 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 and we have another affine, mapping, mapping, mapping. What goes here? Well, maps of affine schemes correspond exactly to maps of rings in the opposite direction. So everything I'm saying on the left is exactly the same as the things I'm saying on the right. And now what goes here is the tensor product. And the definition of the tensor product of rings is that it's, if you want, the coproduct, which means, if you remember what how we cooked it up, that it is the cofiber product, which means if we take spec of it, it is the fiber product in the category of affine scheme. So this is nothing more than a restatement of something that we at least allegedly knew before. Okay, so the next thing is that if we have affine schemes, X, Y, and Z, so say X is spec A, Y is spec B, and Z is spec C, and now we're going to be in the category of all schemes. So W is an arbitrary scheme, and I claim that the fiber product exists in the category of schemes. And the reason what's different now, or why does this work, it's because maps to affine schemes now correspond to maps of rings in the opposite direction. So now we're using this exactly there. And so our map from W to Y and to X, such that they commute to Z, is exactly this map from the data of C mapping A to B, and then both of them map to the rings of functions. And then the same argument as before says we just stick a ring inside here, and there's a unique map like that. And so if you literally cut and paste the previous argument, it means that spec of A tensor B over C does satisfy that.
So Robbie, if you're writing on the screen, we couldn't see it. I don't know if this
right. So do you see the red line turning and disappearing?
No, we're not seeing anything written on YouTube.
Okay, so the red, I was using the
Red thing. Oh, like the circle thing that you do?
Yes, but it's apparently not visible. Is that right?
Yeah.
I guess not. So, okay, good. That just means, well, good to know, not good. But that's very good to know.
The slide also is just the says fiber products in the category of affine schemes. Is that still the slide you are on, or are you one ahead?
No, and now I begin to see what how about now?
Observe. Fiber products of the category of affine.
Unfortunately, observe is the start of every slide for a while.
Yeah, it's just the affine scheme slide, the affine fiber product slide.
Okay. That means, so you're not noticing there's no purple messy writing, right?
No.
Okay. That means that I will remirror. How about now?
Yes.
Yeah, there's a cursor.
Good.
All right.
Ah, great. Maybe I'll actually use the cursor.
I'm gonna.
You see the cursor now, right?
Yeah, it's on the top.
Oh, okay. That's not where I wanted it to be. Okay. Wow. Now you can see it moving.
Now
around.
I see the cursor. Yeah, now you're pointing to O. Yeah.
Okay, good. So now, great. Okay, good. So let me maybe go back. And so, great. So, okay. And so let me know when the arrow, I'm going to actually use the arrow now. And so the fiber products in the category of affine schemes exist. I'm just going to repeat what I said now that I have visuals, which is the statement is about specs. And so, but any statement about specs will just be the same statements about rings with arrows going in the opposite direction. And the fiber product will, the tensor product, basically by definition, the universal property does satisfy the universal property. And then what I said, and now I didn't say it. Unfortunately, I wasn't showing you visually what I was doing at the time, which is now the fiber product of affines exists in the category of schemes. And that's because now we put an arbitrary scheme in the upper left corner, this W, but everything we said works just fine because the maps from an arbitrary scheme to an affine correspond exactly to maps from from the ring to the space of functions. Okay, so so next I'll just observe that now the fiber product exists in the case, we knew it the case when X and Y and Z were affine. Now we'll do it in the case when X, Y, and Z are still affine, and X is just an open subset of something affine that sits inside Z. And I claim that that fiber product exists, and the reason, as a scheme, and the reason why is because I can make a fiber product of X prime with Y over Z, and then I could make a fiber product over X prime with X, but then that's a fiber product of this entire rectangle. That's how fiber products work. Great. So now we've got this slightly more general situation. Great. So next, we could just do exactly the same thing where if I could reverse my X's and Y's and let's, and then this exactly the same argument shows that we can take the fiber product of an open subset of an affine scheme with another open subset of an affine scheme over an affine scheme. So that's nothing more than the same argument again. Okay. Next, we'll do something slightly fancier, which is now we'll do it in the case when Z is an open subset of an affine scheme. It may not be affine itself. So, so we have Z sitting inside Z prime. And now I will show you that the fiber product of X and Y over Z exists. And that's because if you just take I know the fiber product over Z prime exists because that's affine, Z prime is affine, and X and Y are both open subsets of affines. And so this exists, but now I claim it's also the fiber product over Z. And why is that? It's the best reason is to just realize what this means. This is like, what's a map to X and Y that you want to map to, what's a map to X and to Y that agrees over Z? Well, it certainly is a map to X and Y that agrees over Z prime. And conversely, what's a map to X and Y that agrees over when you commute with Z prime? Well, we know they don't just map to Z prime, they map to Z. So, so maps to X and Y agreeing over Z prime are the same as maps agreeing over Z. So I don't know if that's confusing or not. If it's confusing, then I could say something fancier, which if you remember the magic diagram, which is a problem to think about in maybe the first week or so, which is that if you have Z sitting in, you have that X tensor Y or X fiber product Y over Z to X fiber product Y over Z prime, that comes from, that's a fiber product from Z goes to this Z tensor Z over Z prime. But if you have a monomorphism, that's an isomorphism, so this is an isomorphism. So maybe it'll make you feel very heroic to use something very categorical, but it's less categorical. I would just much rather really understand why it's true. Okay, so next next I want to say that X fiber product Y exists in the case where X is the union of two affines. And so here's why it's true. The first thing I need to do is construct the candidate fiber product, and here's what I'll do. So X1 and X2 are two affine open sets that cover X. And I've got the intersection of X1 and X2. And I really find it easier to just call it X12, but I'm afraid that you'll forget that definition, so I won't. And now I do know that the fiber product of X1 with Y over Z exists, and ditto for this by the previous, by what we've already done. And now more than that, X1 intersect X2 is an open subset of an affine. So I even know this exists, and better yet, I know that because what I'm producing is a fiber product, this is an open subset. And so after tensoring, this is an open subset because fiber products with open subsets are open subsets. So I have two things I've constructed, two schemes, and I have an open subset of this that's isomorphic to an open subset of that. So I can glue together, I can now glue these together to get a candidate. I need to put quotes around it because I've not shown you that it satisfies the universal property, but I claim this is my candidate guy, which is this and this glued together. Great. So I can't just do it and assert it. I need to actually check that it satisfies the universal property. So let me now do that. What do we have to check? Well, if we've got a scheme mapping to X and to Y, and they agree on Z, I want to figure out why is there a map to this thing here. And I guess I should put maps like that and maps like that. Well, here's what I'm going to do. What I'm going to do is I will take W and I will have an open cover of W by W1 and W2, where I'm just going to pull back X1 and X2. So if you want it, that's a fiber product as well. So I take the pullback of X1 inside X to get W1 inside W. And similarly, I have W1 intersect W2. And so now I have a map. So because this is the fiber X2 tensor, X2 product Y over Z, that's a fiber product, it exists. That means by the universal property, W2 actually maps there. W1 maps to the corresponding thing, and W12 maps to the corresponding thing. And so I have three things. W1 is mapping here, W2 is mapping to my legend fiber product, and the intersection, and they agree, it's the same map on the intersection. That means that this map from W1 to this and W2 to this, agreeing on the intersection, because maps glue, which again is something we did discuss before, we have produced a unique map like this. So we have shown, you have to digest this, but we've shown that it satisfies the universal property. Okay, so now we've done the case where Y is an open subset of an affine, Z is an open subset of an affine, and X is a union of 2 affines. I will now do when X is a union of 3 affines. And don't worry, things will speed up in a second, which is now the 3 affines case will be when X1 is actually the union of 2, and that's 1. And then you just do the same argument again. If you parse, and everything I said here just works as it is. And then you could do 4 and 5 and 6. But at this point, you might as well do any number. And I could have done this to begin with, but I wanted you to understand the gluing. So if you do this with any number, potentially, I don't mean a finite number, then all that needed to work here is you had a whole bunch of xi's and pairwise intersections and agreements on the pairwise intersections. So that means that we could take any number of affines glued together and we can construct the fiber product in that case. But that's just saying that X is any scheme at all. So if X is any scheme at all, we take the fiber product over an open subset of an affine with an open subset of an affine. But then exactly the same argument will show that this works with the X's Y's reversed, shows that X and Y, you can take the fiber product of any scheme with any scheme, but only over an open subset of an affine. Okay. Now I'll show you the case where Z is the union of 2 affine schemes. And again, I really think it's useful to do 2 before you jump to infinity. Because you can be a little bit careful about what you actually need to check rather than just waving your hands. Okay, so so how will we make this work? Well, Z is the union of 2 affines, and so we'll cut X and Y into 2 pieces by just taking the preimage of Z1 and Z2, and they all have intersections. X1 intersect X2, and Y1 intersect Y2, which is the intersection, which map to the intersection of Z1 intersect Z2. So that was, but then we could take the fiber product of X1 with Y1 over Z1 and X2 and Y2 over Z2 and ditto for the intersections. And then we could define our candidate thing by simply gluing together the 2 things we want to glue together along this open subset where this open subscheme. And so that's it, that's our candidate. And now just to be sure you see I'm not waving my hands, let's check the universal property. So we have X to Z, we have Y to Z, and we have our candidate fiber product, which we've not proved yet. Suppose we have a map, let me do that. And let me also remember to send that back to update the slides. Okay, and suppose we have a map from W to X and W to Y that give you the same map to Z. So the question is, how do we know that there's a unique map to our alleged fiber product? And that will show it's our alleged, that it is our fiber product. How do we do it? Well, we define W1 and W2 as the preimage of Z1 and Z2, and we have their intersection. And then we have maps from W1, because we've already constructed some fiber products already, from W1 to this open set of our alleged one, W2 to this open set of our alleged one, and they agree on the intersection. Once again, we win. That deals with 2. Then we could do 3 or 4 or 5 or 6 and infinite. And again, the jump to infinity, you can't do it by induction, but there's this fact of gluing infinitely many schemes together so long as the intersections and the triple intersections, everything agrees.
You got your cursor again.
Thank you. Good. I even wanted my cursor sometimes, but not now. And that is great. So that's the proof. And something. So first of all, maybe it was long-winded. It was long-winded. It was deliberately long-winded, but almost nothing happened. Almost all that we ever really checked was that we could glue 2 things long opens, or maybe that one fact about gluing infinitely many things together, so long as the pairwise intersections glued as we expected, and the triple intersections we had no problem. So something momentous happened that I want you to understand, because you can use this repeatedly in other situations. And so to help you understand, I feel like I only understand how a proof works if I've actually proved something myself along the same, using the same method. It's not enough for me to, it helps to read a proof line by line, but it's much better if I've used the same idea somewhere else. So here's a different definition that's going to use the same idea, which is, okay, if you have an integral scheme, I'm going to define the normalization of this integral scheme. And so the normalization is something else which maps to it. It's going to be a normal scheme. So we're going to get, just like sheafification gives you the sheaf that is closest to a pre-sheaf, the normalization will give you a normal scheme that's closest to the thing you started with. And so just like sheafification, it satisfies a universal property. And if you think about it, you might guess almost correctly in the first try what the universal property has to be. So any dominant morphism from any normal integral scheme has to factor uniquely through the normalization. So given a map from x twiddle to, given a map from y to x, there should be a unique map to this thing here. And this means x twiddle is defined up to unique isomorphism. And it's essential for these arguments to work that it's defined by universal property. With the fiber product, we use the universal property repeatedly. Okay, so now comes the theorem by a distinguished mathematician that the normalization always exists. And the distinguished mathematician in this case is you. So I want you to be able to prove this completely. And then once you do this, you'll completely understand the proof of the construction of the fiber product. Okay, so how did you prove this, you may ask? Well, the way you are going to prove it is you'll first observe the case of the case of an affine scheme. So if x is affine, and here A is an integral domain, well, we already have the notion of the integral closure in its fraction field. And so if A were already integrally closed, this would be an isomorphism. So you have the integral closure in its fraction field. Then I claim that the resulting map of specs is the normalization. So the normalization, that means the normalization, at least of an affine scheme, exists. Okay, why is that true? The reason is that if y is affine, it's not so bad. If y is spec B, that means it's an integral domain. And if you have a map of rings from A to B and it's dominant, so I'll let you think of what that means, then you have to show there exists a unique map from the normalization, from the integral closure into it. So that's the first thing you'll do. And the next thing is, well, what if y is not affine? And I'll tell you the beginning of the story, which is, what if y is an open subset of an affine? Or what if y is the union of two affines, or three affines, or an arbitrary number of affines? And at that point, you'll finish the proof. So that's what I would like you to actually do, because if you do it, you will understand how the fiber product works. And there are other examples too, such as the reduced version of a scheme. If you want, there's a version of a scheme which has no non-reduced behavior, has no fuzz, has no nilpotence, and you can make the best possible one, and you can describe what the universal property is, and guess what it is. I will tell you, but I almost feel like I want you to think about what it might be. If you have an arbitrary scheme, X, then the reduction is going to be a map to it from a reduced scheme, so that a map from any other reduced scheme must factor uniquely through that. So then it's a universal property, we want to show that it exists. And once you've done the normalization, all you need to do is you realize, well, all you have to think about is what's the affine case, and then starts to say the same sort of thing. And then there are other examples too, which I will, and it's less that you should memorize all these other examples than you simply have one example in mind that you understand completely. Okay, so now that we know what fiber products exist and that they exist, we can define products in general, and just to be clear that they're like fiber products, I could also take them, that's the same as fiber products over the final object of the category. If you want to take products of things over the complex numbers, that translates to this, and people lazily write this as x cross y over c. There are other words for fiber product where people will describe it as base change or pre-image or Cartesian diagram, and it's always just about perspective, how you think about this. If you think about this as like a family of things and you want to pull back to something which may not be an open set, you might call that pullback. Or so there are different words you might say. If you in the special case where you have a scheme Z and a point, you could map spec of you can map the point in, by which I mean spec of that residue field of the point going right to that point. And then if you do the fiber product, this is the reason for the name, is you get something which really is, well, I could call it the scheme theoretic fiber. So that's a definition, but it's what you think it is because you actually get the correct topological space, for example, if you take the preimage of P and you take the actual preimage and take the induced topology on it, you will get the correct topological space. So that should make you somewhat happy, but you have better than a topological space. It has a scheme structure. Okay, so something which may make you sad is that the fiber product is that the underlying set. You might hope that the fiber product you might reasonably define because schemes are sets with topologies and sheaves. And in general, things coming in geometry are described in such a way, and you would think that then you'd hope the fiber product you should construct by taking fiber products of sets and then topologizing them, and indeed there are fiber products of topological spaces, and then by taking the rings and doing something appropriate with the rings. And that's not true. Even the set is not the fiber product. The underlying set of the fiber product is not the fiber product of the underlying set. And the prototypical example is that the line A1 tensor A1 across A1 is A2. And unfortunately, if you picture the geometry, you have like you have a line and a plane and two projections. And the problem is you have all sorts of new points inside A2 because you've got these crazy generic points. So you have things which are, let me change colors, like curves in the plane. And two different curves in the plane, random curves in the plane, will both map to the generic point of the x-axis and the y-axis and map to the same thing here. So that may make you sad, but actually it shouldn't make you sad. This is a feature, not a bug, because certainly it would suck if A1 cross A1 were not A2. You want that to be true. So why should you learn to be happy about that? The reason you should learn to be happy about that is fiber product means fiber product in any category. And the fact that fiber product of sets is the example you first have in mind should be thought of as being misleading, because it turns out that the fiber product of sets is what it happens to be. So anyway, think of this as a feature, not a bug. Okay. So now that we've discussed fiber products enough, I want to go back to talking about morphisms, and I'd like to make some definitions of things, of classes of morphisms, of nice morphisms. But before that, I want to make some general statements about what we're looking for. Normally, if you have a nice class of morphisms, like open subsets, closed subsets, or open embedding, closed embeddings, then they're not going to be they're going to be nicely behaved in some sense, and I want to make that precise. So the first thing I'll say, maybe I'll first give examples before, so you'll have examples in mind. So the examples, we don't have very many classes already, so I'll just give the examples of isomorphisms and open embeddings. These are certainly reasonable classes of morphisms, and they're both local in nature, by which I mean, if you want to check if X to Y is an isomorphism, it suffices to check on a cover of Y, and ditto for an open embedding. So in other words, if it's an isomorphism for any open subset inside Y, then it's an isomorphism, and it suffices to check on any open cover. Ditto for open embeddings. The second nice thing is that if you compose two open embeddings, you get an open embedding. If you compose isomorphisms, you get an isomorphism. That's not shocking. And any notion of a nice morphism that doesn't satisfy this doesn't deserve the name nice. And the last thing is, now that we have the word, or it's preserved by fiber product or base change or pullback, meaning that if you have, for example, an isomorphism X to Z, it pulls back to an isomorphism, but that's obvious. And ditto for open embeddings, I wouldn't say that's obvious. That was our first observation. So things behave well under pullback, and that was, I should say, already somewhat implicit in the local nature, because that means that if X to Y is nice, then any preimage of any open subset to it is nice, because that is an example of a fiber product. Okay, so those are, I'm going to observe that those are nice, and I'll give you next an example. So let me define the notion of a quasi-compact morphism. You already know what a quasi-compact topological space for scheme is. A quasi-compact topological space is something for which it's half of the Hausdorff. It's a finite subcover property. Every cover, open cover, has a finite subcover. That was the definition of quasi-compact object. And now what's a quasi-compact morphism? It's that if for every affine open subset, the preimage is quasi-compact. And so so that requires checking every single affine open subset. So that's a pain. But the claim is that it suffices to check on any affine cover. So how do we check that? Well, we have one of our favorite things we'll use repeatedly again is the affine communication limit, and we'll do that in a second. But I want to point out what we did is we turned the property of a scheme instead into a property of morphism of schemes, and that's what this is the notion that I mentioned before of Grothendieck's. I'm sure this predates Grothendieck, but the idea of taking properties of objects and turning them into properties of morphisms. Okay, so how's a proof going to work? Well, we have to check two things for the affine communication limit to work. The first thing is that we have the first direction is if the preimage of one affine is covered by finitely many affines. Why is it true for a distinguished open as well? Well, the answer is that if you are localizing at F, let's see if I am going to let me put this here. Great. So, yes, sorry. And that means if we're inverting F, then it's covered by finitely many affines, where I simply localize, I throw out where F is 0 in each one of these. So in other words, the inverse of spec B is covered by M affines. When I take a distinguished open, it's covered by M affines, and each of them is distinguished in the thing upstairs. The second thing we have to check is that if spec B is covered by finitely many affines, and that means of distinguished opens, and you should always immediately say in your mind, that means that these elements generate the ring. Then we want to show that and if we already know the preimage of each one of these is covered by finitely affine sets, let me call them this, then I claim that the preimage of all of spec B is also covered by finitely many affine sets. Well, that's true just because there are finitely many of them. There's finitely many of the Fs, and each of them has finitely many AIJs. So we're done. That's the proof. There's nothing else to do. And so you can check that this is a reasonable notion that it's local in nature. That was the affine communication lemma. Preserved by composition. Well, if you have a map of X to Y to Z, and both of these are quasi-compact, well, I'll check that the composition is, well, the preimage of an affine in Z is finitely many affines in Y by quasi-compactness. The preimage of these finitely many affines in Y are each finitely many affines in X. So that's also finite. And that means that the preimage of an affine in Z is the union of finitely many affines in X. So you can check that, and then I'll also let you think about why that's preserved by base change. Okay, so great. And then you apply this repeatedly. For example, we had the notion of a scheme that's locally a finite type over the complex numbers, say, or over. And now we relativize that notion by saying a morphism is locally a finite type. So there's our morphism from X to Y. If whenever you have an affine going to an affine, any affine going to any other affine open, then A is finally generated as an algebra over B. So that is relativizing the notion we had before. And maybe that's frightening because you have to check every affine mapping to every affine. But you have to, so you want to check that it suffices to check on an open cover of X and Y, and you don't get any prizes. I'll give you a prize by realizing it uses the affine. You can do that with the affine communication lemma quite reasonably. You would then also want to check that this satisfies all the properties you want, and that also will be cheap. And then this will relativize the notion. And this I should say, even if you only care about absolute things, somehow this tells you it was a right notion because it does relativize. The thing you have described absolutely happens to satisfy things related to the affine communication. Well, that will be, I'm sure that was incomprehensible, that last sentence, so I'll ignore it. And then you can define anything like finite type is locally finite type plus quasi-compact. That works for morphisms. And the very last example I want to do today is the notion of an affine morphism. This is going to be an important notion. And I think it's maybe slightly underappreciated why it's an important notion. And the reason is that a lot of things are going to be built on top of this. Before I start, well, the definition is fast to say, so I'll say it right now. An affine morphism is the relativization of an affine scheme. So that already tells you what the definition is, in the same way that finite type was determined by our absolute notion of what a finite type scheme over a ring is. So an affine morphism should affine locally look like an affine scheme. So translation, for every affine open subscheme of Y, the preimage of that affine should also be affine inside X. So given that affine schemes are the fundamental building blocks of all schemes, affine morphisms should be something you realize are super duper important. So that's our definition. And it looks like I'm going to say everything just like I did before. And indeed, the strategy will be exactly the same. So I've made my definition, but then my claim is that it's enough to check this affineness on any affine cover of Y. So otherwise, it's kind of a useless notion, because how would we ever, well, not that, how would we ever check it? So how do we prove it? Well, you're not going to be surprised that, but I will give you a prize, that this is that you'll prove it using the affine communication lemma. So what do we have to check? Well, there are, again, always two things to check for the affine communication lemma. It's going first from an affine to a distinguished open. There's an affine distinguished open. And second, from a cover by finely limited distinguished opens to an affine. So let's check this. And once we do that, we'll be done with the notion of an affine morphism. So we have a map to, so the preimage of an affine is an affine for spec B. And the question we want to check is we take a distinguished open subset. So that's, let me change my color. If we take a distinguished open subset, why is the fiber product also affine? And the answer is because we already know what that fiber product is. We checked even before we knew what fiber products were in general. We knew that the preimage of the locus where f is non-zero is where the preimage of f is non-zero. This was back to maybe even the first time we were talking about geometric spaces, if you remember. So in other words, it itself is even a distinguished open subset, but in particular, it is affine. So that's really cheap. That's great. And so what's left to do? Okay, so now part two, we have to check is if you have an open cover, an affine open cover, a finite distinguished affine open cover of spec B. So translation, if we have B is generated by n elements, and I tell you furthermore, so we have X to spec B, and I know that the preimage of each of these distinguished opens is affine. So in other words, X, the X restricted to the distinguished open is spec of some affine ring. Then I want to conclude that X is affine. Once I do this, game over, I proved that the hypotheses of the affine communication lemma hold. And so why is this true? Well, the answer, this is actually surprisingly, if I say hard, I fear you'll have the wrong idea. What I mean is it really requires one extra insight that's not immediately obvious. And in general, when you use the affine communication lemma, you want all the insights to be obvious at least once you have seen a few tricks. So the question is, what is the missing trick? And so next time I will tell you about the quasi-compact, so the QCQS lemma. So let me conclude by just saying that you are now free to understand many classes of morphisms. So let me give you the example of a finite morphism. And so a finite morphism is defined to be an affine morphism. This is, and awkwardly, we need to know what an affine morphism is first, such that, well, what do we need to check? What's the definition? Well, an affine morphism locally looks like spec A goes to spec B. So this is B is mapping to A as rings. I want A to be a finite B module. Finite B module. And I would, so what this means is it's finitely generated not as an algebra, but as a module. And I guess this is something where I believe there's a linguistic issue here where I suspect that in French, there's a phrase that's constantly used, which I think is it's good to have a phrase for this. In English, we don't use it, I don't think, which is the notion of finite type. So it's a finite type B module, by which I mean it's finitely generated as a B module. So that's what a finite morphism is. You can similarly define an integral morphism if it's an integral extension of rings. You can have examples such as the normalization is always an integral morphism. It's always an affine morphism because you built it affine by affine. And so you're now free to just read all these various definitions. And the one unusual definition is that of a quasi-separated morphism. And a quasi-separated morphism, well, you already know the definition if you've been listening to what I've been saying, and the definition you would come up with is correct, which is that a map from X to Y is quasi-separated if for every affine in the base, the pre-image is quasi-separated. And we've already defined quasi-separated, which is that the intersection of two quasi-compacts is quasi-compact, or the intersection of two affines is a finite union of affines. And that's our definition. And again, this, as with the others, you can check is nicely behaved. So basically, any reasonable morphism after this one trick of this QC/QS lemma is going to be complete, you now know enough to understand. But there's a much better definition. And this will also lead us to Hausdorff as well. And this will lead us to the insight of next week, which is now that we have fiber products, we have the notion of a diagonal morphism. So if you have a map from X to Y, then you also get a map from called a diagonal morphism, diagonal sub pi, which sends X to X cross X over Y. And what's the map? Well, by universal property, we have an isomorphism from X to X and X to X. And that means that corresponds to a unique map from here, from X to the diagonal. And lots of things turn out, to my surprise, and in the end, pleasure, to be properties of the diagonal morphism. That's where Hausdorff is going to come from. So the thing I want to end with is both that this is going to be the favorite topic of next time, but also to try to find out why I should not have been surprised. So if elsewhere in geometry, people are not surprised that the diagonal morphism is the right way to define lots of things or to understand lots of things. So that I'm curious. So now it's almost 9. So now would be a good time for us to stop and pause and see if there are general questions. And I will let, I'll move my cursor out. I will make sure I can see. Not sure if I can see people, and one moment. And I think I can, okay, that's good enough. I can already see lots of things that make me happy. Great. Now I'm ready for.
Okay, so I'm here.
Yep.
So we just caught up. So sorry, I have allergies, so I'm might be a little stuffy. Yeah, so I have some questions. So one thing that I think was maybe used but not mentioned before was the morphisms to affine schemes in that adjunction. I'm not sure if we talked about that.
So I did at least mention it, but did not make a big enough deal out of it, partially because you wouldn't, partially because it's something you will appreciate more now. So just to say it again, right, the statement is that what are morphisms to an affine scheme, that this is exactly the same as maps to functions. So this, I will say, this is an exercise, and it's a gettable, but it's an entirely gettable exercise, but not immediate. And so this is a really useful fact. And maybe a related thing is the let me just to try to motivate it in complex geometry. So in complex geometry, if you have an open subset of c to the n, for example, and I asked you if I have a manifold to and I wanted a map of a complex manifold and map it to you, I claim that is exactly the same as taking n functions on M that happen to, well, I guess n functions on M certainly are the same as maps to C to the n. And so n functions in M that map to an open set are n functions to M with some condition. So the statement is that when you map to something that is affine in some sense, you could recognize it purely on the ring level, on the level of functions on your entire, no matter how complicated the topology of your manifold is, for example.
Yeah, I think in the sheaf definition of manifold, that's baked into the definition too. Yeah.
Yes.
Yeah.
And really here it is too. Right. Actually, that's a really subtle point you're saying. I mean, it doesn't sound subtle, but it's very subtle. That here it's baked in too. And the great thing is it sounds like it's right. It's an exercise, and you do it and you think, well, wait, there's nothing there, which is a sign of good baking.
Yeah. Okay. So here's one thing that I wanted to say that some people get confused about is P1 cross P1 versus P2. So I think some people
P1 cross P1
that they're not
versus,
the same.
Right.
The P2 is not.
I guess I almost would say. Yeah, I would almost say. Why would you think? No, I do. I would want to say there's no reason to think they're the same. Or I'm not.
Well,
sure
I mean, in every other subject in math, whenever you write a superscript, it usually means a product of several things. So
that's true. But how about like a circle? Like, okay, except S1 cross S1.
Oh yeah, that's good. That's a good point. That's a good one.
Right. So that's yeah. So I guess that's not.
It's true. You're right.
So I think maybe that's good. That's
another good example of bad, or I don't know.
Yeah. So it's a feature of both of these are a feature of geometry, not in particular of algebraic geometry. I mean, that's, like RP. What's true with that's true.
Yeah. Okay. So one thing that I had to talk about also was a global spec. I mean, I think you were referring to this too, maybe alluding to this why affine schemes are so, or affine morphisms are so important. I don't know if you want to.
So what you're saying is the following thing, which is we absolutely could.
You can do factorization as well. Like if
what's that?
Factorization of morphisms.
I don't know what you mean, or in which way?
So like, you can always take, so if you have a morphism, you can always push forward the sheaf, right? And then do global spec. And you can always factor it into an affine morphism followed by.
So, okay, so let me say that in the following, right? So these are, so if you have an affine right? So if you have
any
an
morphism
affine scheme.
Yeah.
Then you have, of course, you have spec of it. That's what we cooked up. Now, if you have an affine morphism, this suggests something interesting you can make up, which is here's y to x. And for each open set, for each spec of downstairs, you get spec upstairs. And this is a B module. A is a B module because A is a B algebra. It's a B, well, what is a B algebra? It's a B module with an algebra structure. So translation, or translation, which will now require a little bit of thinking, this is now a sheaf of algebras, not just so it's a sheaf of O modules. So this determines a sheaf on Y of O modules. And over a spec, it's one of these M twiddles. So so a lot of ideas we've discussed are present here, and we could absolutely talk about them now, and they involve gluing together or taking fiber products of a bunch of ideas that you've already seen. So So rather than connecting all of them, there's nothing new you haven't seen, but I'll use the words that we've not described, which is there's the notion of a quasi-coherent sheaf. What is that? That's a module. That's the globalization of a module over a ring. In other words, for every ring I want to have an A module, and I want it to behave in a certain way. So this is a quasi-coherent sheaf is not the same. It's a special kind of O module. It's something which comes up in the way that we describe as an M-twiddle. So that's a notion that's already secretly there. That's also going to involve the affine communication lemma. And then secondly, then you can have a quasi-coherent sheaf of algebras. And that will produce for you, by taking spec over spec B, you would take spec of the corresponding algebra, I'll call it A, and then that will glue together well, and that will relativize the notion of spec. That'll be spec of the sheaf of algebras. And then the notion of a finite morphism, and someone had asked about why finite morphisms are defined to be affine, and I'll say it maybe in a little bit. In this case, you take spec of a finite type sheaf of algebras, quasi-coherent sheaf of algebras. And this is just there's no, what's new here are the words, not the content. And so all it is saying for every affine, the sheaf of algebras is going to be one of these where that looks like an M-twiddle. And it's going to be over an affine, the module, it's going to be a finally generated module. It's literally a translation. So the way I think about algebraic geometry, I used to think about it is you start with the ground and you build this very complicated thing that's going up and really far. And instead, it's like in high dimensional space. And you have all these very short things, and then you somehow have to take this and this and this and this. And once you combine all these epsilons together in different directions, you get very complicated things, such as thinking of, so translation, finite morphisms correspond to finite type sheaves of algebras in a strong sense. Okay, now I've said too much, so I will stop talking about that.
Okay. So another discussion that came up was if you could apply this proof to products of manifolds.
Yes, I don't understand otherwise. Yes, great. So here's something which I didn't realize until learning about schemes, because I was wisely misled by people who taught me about manifolds, which is that if you have two manifolds and you ask what the product is, I would say, oh, that's obvious. You just take an atlas of the first, an atlas of the second, and you blah, 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 blah. And that would be right. But how do you know that if I cut it up in a certain way and you cut it up a certain way, we don't get different things? And the answer I would have said when I was younger is, oh, yes, you just take smaller atlases and something, something, something. But instead, this works for manifolds, right? This works for manifolds, or complex manifolds, or complex analytic spaces. The point of this robust description is it works for once you know a bit more, algebraic spaces. It works for tropical Berkovich spaces. There are all sorts of things where you show products exist by just showing they show locally, they exist locally, and they are sheaves.
Yeah. Great. All right. So another thing that I had was at one point, this is kind of unrelated to the kind of theme, but at one point you took spec of a residue field of a point, and then you identified it with the schematic point, right?
Yes.
Right. And I don't know if you want to say something.
Maybe, sure, that is good. So there are a couple of cases, and these are going to be there's a series of exercises in the notes about this, which is if you take a target, let me just go back and make sure the slides are updated or refreshed. If you have, so we already know that this brutally important fact that maps from an arbitrary thing, I'll say scheme, but manifold or complex analytic space, to an affine are easy to understand. And I vaguely emphasize that the opposite was not true, except sometimes it is. And I'm going to just mention these examples. The first example is if you take a field, spec of a field mapping in, well, all you need to do is find a point. So this is something you need to actually check. Find a point whose residue field is a subfield of the field here, and you will get a map. That will determine a map in this direction. And the special case is that if you take the actual residue field, that's the thing which deserves to be called the point inside X. So it's not just of course, when you say the point, you don't want it just to be a point, you want it to be a scheme, which means it's got to be, well, as a topological space, it's obvious, but you need to say what field is involved. So, and the other thing that's really useful is that if you even map the stock at P in, and that's mapping the affine in, and that's a really useful thing to do as well. So the exercise is that there is this canonical morphism, meaning a morphism with no choice involved from this affine thing into here. And I should say, how do you do it? You might as well, you would even map it into an affine open. I'll let you think about the exercise because there are different ways of thinking about it.
So if you have the image of an affine scheme, is it always contained in an affine?
Great question, right. So a weird thing is an image of it, right? The image of an affine is not necessarily even contained in an affine, and I'll give you a proof. So P1 is the union of two A1s, and if you just take the union of those two A1s, that's affine, and that surjects onto P1, which is not affine. And in general, any quasi-compact, anything covered by finitely many affines, that means it's a union of finitely many affines, but then it's surjected onto by the disjoint union of those affines, which is the same as a single affine where you take the products of the rings. So in fact, it's almost massively wrong. And there's this trick called Zhuanglu's trick, where Zhuanglu is one of the, right, Grothendieck had approximately 12 disciples, and you can decide who he thinks the analog of Judas is. But Zhuanglu is one of the disciples, and so this is a trick of his, that where you prove things about projective things by taking a very cleverly designed affine covered by a single affine.
Yeah. Okay. Okay. So here's another question. So is there a notion of, so people were talking about how we add the adjective locally. Is there a notion of a locally finite morphism?
So yes, but right. So locally often has, locally would mean something, the way in which we're often using locally, but this is not a hard and fast rule, is not what I mean now. But finite morphisms are affine, but you might say, what about something which just has, oh, one thing I should say is finite morphisms. Actually, let me answer that question second, because this forced me to think about finite morphism. I did not say something, which is if you have a finite morphism, I claim the fibers that that above each point, they're only finitely many points. Here's my proof, knowing what we know already, which is just take spec of your field, of your residue field, and by the fact that finite morphisms behave well under base change, one of our definitions of niceness, then we must have spec. It's affine, so it's spec of something. It's finite, so it's a spec of some algebra, which is a finite dimensional vector space over our field. Let me call the field lowercase k. And you can check, if you're using some algebra, that spec of any finite dimensional vector space over a field, like any algebra that's finite dimensional, it can only have finitely many prime ideals or maximal ideals. It's what's called an Artinian ring, and therefore there are only finitely many points above it. So we've just proved that finite morphisms are finite to one. And then you might say, well, okay, but what about, is that the same thing? And the answer is no, there are things which are finite to one, but not finite. And so maybe that's a thing which might be almost called locally finite. So there's a notion of quasi-finite, which I can define, which is, okay, and this is the one case where do not read Hartshorne's definition because it's incorrect. It's a different definition than other people use. And what quasi-finite means is finite fibers, which is, I guess, the definition that Hartshorne gives, but plus it should also be locally finite type. That's the, I hope I'm not forgetting finite. Okay, I think that's right. I have to remember the locally or not, but you can look it up in the notes or anywhere.
And then I think one thing we haven't mentioned yet is the degree of a map.
Is it
Yes.
quasi-compactness and quasi-finite? So
Okay, finite type. That's the thing I was trying to remember with the local
Yeah.
chart. Is that better?
I'll check. I'm
Yes.
having doubts.
Yeah, my question was about the L, which I carefully wrote messily enough that I was hoping it was not there. And you could, I should say that Jonathan's checking, we're asking not because we're just being pedantic and wondering what it was. There's a reason why you want this definition to be this and not just finite fibers. For example, you want it to be preserved by base change. Yes, and that sounds to me like
Yeah, it is finite type.
So you want your notion, this is a great example of those properties you want to have true, which is you want a nice notion of a morphism to be preserved by base change. And so in particular, finite fibers is not preserved by base change. And the answer is actually one that actually Jonathan mentioned 1 or 2 weeks ago, which is Q bar tensor Q bar over Q, or spec of it. That's a fiber, that's a product of spec Q bar to spec Q, spec Q bar. And you'll notice that this morphism is, that's 1 point, that's 1 point. That's got finite fibers. That's 1 point. And this has infinitely many fibers. The points kind of correspond to the Galois group. And so finite fibers does not behave well under base change. However, this is not finite type. So this is adding this to it. Actually, this is quasi-compact. So that's one reason why you want to add, that's why these three definitions, the three properties help guide what the right definitions should be.
Q-bar.
Another example, something which is the notion of surjective morphisms is preserved by base change. So that's a nice notion. The notion of injective morphism is not preserved by base change, as this example once again shows you. That's injective, but this is not injective. So
I don't think you've
that
said
means
what
that
surjective morphism
What's
is.
that, Peter?
I don't think you've said what a surjective morphism is yet. Have you?
Oh, sorry. Surjective just means surjective on points.
Yeah.
And yes, that's a good point. So surjective, I just mean on points. And injective, I mean just on points. And surjective, I can define them, but you should never, but the lesson of today is that you should be happy with the notion of surjective morphism because it's a nice morphism. It's local, it satisfies those three properties. And you should not be happy with injective because it's not preserved by fiber products. And you should not be happy with finite fibers. And it doesn't mean that you should give up on the notion. When you, instead of giving up on finite fibers, you realize the right notion is finite fibers plus finite type at some point. And with injective, you realize at some point the right notion is well, this is gonna sound very lame, but a way to fix injective is you're sad because injective is not preserved by base change. You say, okay, I'll just define a notion of things that are injective upon any base change, and that's that. So, which is called universally injective. Another example is something which is a closed morphism. The image of a closed is closed. Well, that's not preserved by base change. So you toss in universally closed, things that are preserved by all. So when the universally means after any base change, and now we know what that means. And if you feel like that's not, if you feel like people will laugh at you because that's too simple an idea, then you use the word.
Yeah. And then everyone
Exactly.
forget what it means.
What's that?
No, then you forget what it means.
Yeah, but you can really impress people by. I feel like I was a very, anything that's French sounding always is impressive. Whereas but all it means is universally injective.
Yeah.
Okay, I think. Wait, did I even answer the question? Or I went sideways.
Yeah, we went beyond. So what was the question? The question was about finite. So I asked locally. I asked why there was no locally finite.
Right.
And
there are various things that might be reasonable to think that are finite. We have discrete fibers or integral or local. Yeah, so absolutely it's a reasonable notion, but there are different ways you might try to, but finite ends up being the one that matters very much.
The one thing I think you didn't talk about was degree, but I mean, that's, yeah.
But now great. So if you have a finite morphism, because the great thing is we just defined finite morphism literally just now. So we couldn't talk about degree before, but now that we have, if you have a finite morphism, then I will define the degree at a point P. And the answer, what the degree is not the number of preimages. In topology, that's not what degree is anyway. What it is the number of preimages counted correctly, just like in topology. But what does that mean? It means take this and take the dimension of its vector space. And that's the degree. And that's the the reason for that notion, the reason I make that definition, or the reason that definition is made, let me give a really useful example I find very enlightening, which is I'm going to take double cover of this. You'll see this in the notes repeatedly because so many things are a part of this. You take the x-axis, so I guess that makes this spec of k join x, and you take the parabola double covering it. So it's k join y, and we'll send y to y squared. So x goes to y squared. The ring map is like that. So so that double covers it. And now we can say I want that to be a degree 2 map. So over the complex numbers, let's say C is the k. We're working over the complex numbers. You can check that over every point. Well, in fact, what is this k as a ring? This is k join x plus y k join x. In other words, every polynomial in y has even degree terms and odd degree terms. And so that means even degree terms you can write as polynomials in x, and the odd degree terms you can write as y times a polynomial in x. So this is finally generated. So ky is finally generated as a module over kx. It's got 2 generators corresponding to the degree being 2. And for every value of x, the vector space is a 2-dimensional vector space. If you look at what the degree means. And so you always get 2. And that makes you happy because you visibly see 2 preimages over, say, the number 1. But over 0, you only see 1 preimage. And you get the scheme k adjoin y mod y squared. And that's telling you that there's a multiplicity of 2 there. So the notion of degree is telling you something correct. And now if you make things even weirder and you work over, say, the real numbers, that's a very strange field for me, then over -1, there is a point. And that point, if you take the fiber product and say what that means, that's r adjoin x mod, we're setting y equals -1. We're setting x squared to be -1. And there we go, that's a point, that's the complex numbers. And that counts for 2. That's why I still count that as being 2 preimages. That's 1 preimage. That's because there's a field extension of order 2. So the 2 comes here because of, above 0, it's because there's a ramification. And here because it's a field extension, and here there's
a word.
And if you're a number theorist.
What does ramification mean?
Great, good question. It means that. It means notebooks. It means things you can say. And unfortunately, I can say that in various different ways. Yeah. And if you want more ways to think about saying it, think about the rational numbers instead. Do this over with the rational numbers, and then you get interesting things because above 1, you get 2 points. You're solving y squared equals 1. Over 2, you get a field extension. Over 0, you get ramification. And over -1, you get a field extension. And if you're a number theorist, or you've seen some algebraic number theory, you'll have seen this formula saying that if you have how do I want to say it? What version I want to say? Even ring of integers in a number field, then if you want to factor a prime, it factors into a bunch of things where the quote multiplicity turns it right. You can have ramification, which is defined in a different, perhaps that's said differently, or you can have a bunch of different, you can have 2 different prime ideals, or you can have 1, but its size is twice as big. And you have the notion of if it's Galois, then the size will be, there's everything you said before in algebra language or arithmetic language now makes sense in this finite, in this language of finiteness. And one reason why I want finite morphisms to be that and have them be affine is that I would not want to throw out a point because that would ruin my count. And so I want it to actually be, so I definitely, I want the definition because it captures something I want to capture. And if I want to capture something else, I'll just have to use a different word.
Yeah. This is great. So one person asked, what's so fibery about fiber products? So
So the question is what fiber mean? And I guess I've come to I've said it so often to myself that I kind of believe it. But I realize it's not really super justified, that if you have a map from something to something else, just of sets or of topological spaces, the idea is that, I presume this is right, that the picture that you're supposed to have is that above a point, the picture is that if you remember X and it's mapped to Y, it's kind of, you have the thing that look like, I don't know, fibers, that it looks vaguely like fibers. And each fiber, the fiber above a point are the things that map to the point. And so that's the reason for these being called fibers of the morphism, I think, or at least I retroactively have believed that that's why they're called fibers, or maybe there's some deep linguistic reason why. And then the fibered product, well, then if you take a fibered, let me change, I'll use different letters than I used before, that the fiber product, well, what you're doing is over every point, you're taking a product of the fibers. So you get something which also maps to Y. And what's the thing? What maps to a point of Y? You're mapping the fiber above that point in X across the fiber above that point in Y. So you get, so it is the fiber product is, its fibers are the products of the fibers. So I guess you could call it the fiber product is the fiber product, fiber. And for short, you just call it the fiber product. I get confused as to whether it should be called a fiber product or fiber product, or you're going to choose your spelling depending on what country you're in.
Oh yeah. It's true. Right. Everybody has a different spelling.
Fiber diagram.
Okay. Yeah. Pull back.
Pull back. Yeah. Pull back implies your which like orientation, which way you're pulling back.
Yeah. So let's see if there's anything else that we. Jonathan asked about this.
I've got, yeah, I can ask
Yeah.
my question.
Actually, Jonathan, is it really true that quasi-compactness is equivalent to surjection from an affine scheme? I'm not sure that's true.
Yeah, because as soon as if you're, I mean, you need relatively affine, I guess. If
okay,
we're talking about a relative map. Now, if you're just talking about a quasi-compact,
okay, relative map is different. That's then I'm happier.
But yeah, just a scheme if it's quasi-compact, it's a finite cover by affines, so it has you take the disjoint union and that's cover.
That's a good point. Yeah, you're right. No, it's at the direction I was concerned by. That if you have an affine, a map search of an affine scheme, that it must therefore be quasi-compact.
Oh, but I mean, it's an image of a quasi-compact. So.
Oh, you're right.
No, the question is, so in schemes you have a final object, and so if you have a final object and you've proved the existence of fiber products, then you get all finite limits.
I think you need equalizers. I think you need equalizers in products, and then you have. Oh, is that the same thing as fiber product? So I think if you have equalizers in products, then you have all limits.
Yeah, you can get equalizers by fiber products with the diagonal.
Okay.
And there you go.
Yeah. That's a good point. That's a good point when the separated, because I always think separated should be defined in terms of equalizers. But anyway.
Yeah, I agree with that. The question is, well, what about all limits? I mean, what?
Oh, okay, that I think the right person I would ask that question to is you. I mean, I
No,
know
the right person is Taylor.
Well, okay, so infinite. Yeah, so I said this before, that infinite products, if you have a quasi-compact, quasi-separated scheme, and the infinite product of schemes exist, right? Then you know that all but finitely many have to be finite. But that's I learned that off of Math Overflow from like Bradenberg, right, Martin, and so but yeah, I have a YouTube video on that. So it's 40 minutes. So I was gonna. But it uses descent. Yeah.
Yeah, you said all but finitely.
I don't. To be honest, I don't even remember.
You meant all but finitely.
Yeah.
And if people are curious, flat descent already happened without us really noticing it last week or the week before. Yeah. And I could sort of say, right, it just as with the fiber product example, where it's secretly, you could describe it as talking about Sheaves and Zariski topology, the descent argument we did for, I guess, the structure sheaf applies perfectly well for flat descent as well, if you just squint and say things slightly differently.
Mm-hmm. Yeah. I mean, I don't really have much else. I mean, I think you said something about fiber product. You informally said you were talking about fiber products of ideas. And this kind of, I think, is a little revealing to how you think about fiber products, and
Right.
how you kind of take two things and match them over some common thing, and, you know, build up. But I don't know.
It's
if you want
true.
to
I really feel like it's certainly true that I've heard algebraic geometers use that phrase as well, and because it's very, it really captures something. I don't know how to say in some other way. That often that you'll hear about a paper, and you'll hear about one version which is an extension a certain direction and something another direction, and you want to ask what the fiber product goes. You want to see what happens. What if we add these two complications at the same time, or two interesting things at the same time? How do they interact with each other?
Ooh, I've got a good one. So one thing we haven't talked about yet is how to take a generic fiber of a family, or how to take, I mean, you've mentioned it very briefly, is how to take, you know, special fibers and generic fibers, you know, and like what does that have to do with base change or fiber products, I should say. Yeah.
I guess the way in which I've set things up, they by definition are fiber products.
Yeah.
I guess. So I don't.
Yeah. I just wanted to point that out for people who did.
Yeah. So until today, we couldn't talk about that. Now we can. You can ask about. You have a family of conics. If I say here's a conic, something you might think about a long time ago would be maybe if you're interested in just conic sections. There is a universal conic section, and it's parameterized by 6 space maybe, where with coordinates A, B, C, D, E, F. And inside 8 space, it's cut out by this equation where the coordinates are A, B, C, D, E, F, and X and Y. And the fiber above, so you have I would describe this as some sort of conic bundle in some sense over A6, which is over a point of A6. In other words, pick, let's say a complex value point. So just pick 6 complex numbers, or I should say real maybe. Then you take the corresponding conic. And so you could ask about specific conics, which are fibers over individual points. Or you can ask about things like the general conic, which would be over the generic point of A6. Or you might even ask about the general conic, the generic conic that happens to pass through various points or is tangent to something. You now have the language to talk about these things. Although if you want to understand, if you want to develop intuition, to turn what you already think into intuition, then you have to just do some examples. And so in that case, doing exercises or doing some examples seems like a very important thing to do.
Yeah, and I guess this also touches what happened with the very, very first lecture, where we were talking about universal, I don't know, did a universal family appear in the first lecture? But that is also,
yeah, nice families and moduli spaces, right?
Yeah, and so if you do have these things with universal families, then, you know, whenever is pulling back this universal family is also a fiber product. So it's
right.
Yeah.
Right. So anytime you use the word pullback, it is that. And you want to say what I've just described as the universal conic in the plane. And so what that should mean is anytime you have a family of conics, then you should get a map to A6 telling you what that, well, actually, that's not quite true, right? But let me mod by scalars. But even that is not well defined yet, because what do we mean by family of conics exactly? You have to say a little bit, and then the word flatness is going to come up into this, whether you like it or not. Well, actually, you can avoid it, but it's close to being forced on you.
Yeah. Okay. So I mean, I think that's all I have.
That sounds good. We're about 9:30, so that's a good our time and Pacific time, so that's a good time too. So
Right.
In that case, let me say that I will. The good thing is I don't need to trim these necessarily, so it's available. I do intend then to post soon to tell you what problems are interesting and why and what to try. And feel free, or please do ask and follow up and ask me things. And even if I'm slow, if I'm too slow to respond to you and you're already moving on to other things in your life, hopefully other people will still benefit from my eventually answering. So please do, and also please do catch anything that helps your understanding that I did not say or that's not in the notes. Tell other people and tell me too, because that's in some sense, everything I'm saying I learned in this way from someone else. Okay, so let us call it a day, and we'll meet for the second or third last meeting of this, at least episode next week. So thank you all. Thank you very much, Shepherds, in particular for being here. and YouTube.